Hello and welcome to NPTEL course on AI/ML in materials engineering. So today we'll deliver lecture 33, which is density functional theory, and I am Professor Tarun Kumar Kundu. I am giving these two lectures on request from Professor Kishanu Vishwas from IIT Kanpur. I am from IIT Kharagpur from Metallurgical and Materials Engineering department. So in the last class we have given the introduction about whole gamut of different methods there for materials modeling, and there also we have said that for very fine size particle, maybe in the range of few angstrom, we need to go for electronic structure method or ab initio methods, and under this ab initio method the most used methods is the density functional theory method. Okay, so I'll give you only the basic principle behind the density functional theory method. If we have to discuss in details, then it require at least 10 lectures. Okay, so I'll give you the basic principle and where AI/ML is used mostly in the DFT DFT formulation. So we'll start from the very beginning so that you get a general build up of how this density functional theory method works. So essentially you need to know a little bit about the quantum mechanics, and also we'll just give you very brief on the quantum mechanics, Schrödinger equation, and the method for solving by using first method of approximation was Hartree method and then Hartree-Fock method. And there is a connection between these Hartree-Fock methods and density functional theory method. So that's why if you have to know density functional theory, also you should have to have little bit idea on the Hartree-Fock method. So in the Hartree-Fock method, essentially it is based on two theorems by Hohenberg-Kohn and Kohn-Sham equations, and their main part played is by the exchange and correlation functionals, and these exchange and correlation functionals are known, but the theory says that if we know this functional form, then we can model all the material property at ground state, and here the AI/ML can help it to find out the better functional. And of course DFT functional calculation are also some of the approximation to the Kohn-Sham equation or quantum mechanical equation. So for solution requires some approximation, and also some of the practical consideration also we need to do to cut short the number of atom we need to treat, at the same time also number of electron we need to treat. So some special consideration also we need to do, and for that generally you need to know a little bit about the solid state physics and all. Okay, so these are the keywords for today's lecture: quantum nature of electrons, then dual nature of electrons, basically the de Broglie principle; uncertainty nature of electron, basically Heisenberg principle; Schrödinger wave equation, the wave function, what should be the nature of the wave function; then how we can solve the Schrödinger equation by using one electron model, essentially the average field method by Hartree-Fock. And also in order to have the antisymmetric property, also we need to use the wave function as a kind of, you need to take the wave function as a Slater determinant, and the solution is generally done by some iterative method which is called self-consistent field methods. And then we discuss about the density functional theory, and electron density is the main parameter, which instead of wave function as wave function in Hartree-Fock method, in this case we use the electron density function. Density is the main parameter in density functional theory, that's what the name is. And functional means here instead of a function we take a function of a function. Okay, so the electron density is a function, and then we take the function of the electron density to get the number. Number means some of the observable parameter like energy and all. So what's the Kohn-Sham equation, then exchange correlation functional, some of the, I'll give you the brief on the iterative DFT procedures and some of the practical considerations. So we'll start from the definition of first principle methods. Essentially the electromagnetic force is the very governing force of nuclei and electrons, and it is predominant in determining the structure, reactivity and stability of the materials. And if we can accurately describe this electromagnetic force, then all experimental relevant properties and phenomena for materials can be calculated without the use of any parameters. That means we don't need to supply any external parameters. So that's why these are called first principle or ab initio. Ab initio means from the beginning. Okay, so just in the system we can make up with what are the different atoms are there, and from there it should give the structure property, reactivity and all. So, the governing law for the small particle is known as the quantum mechanics, not the Newtonian mechanics. Newtonian mechanics cannot deal with these subatomic particles. So, unlike classical mechanics, which is inadequate for explaining the phenomena in the subatomic scale, and the theory of relativity, theory that established single-handedly by two individuals, like classical mechanics by Newton and relativity by Albert Einstein, quantum mechanics was completed by fitting many pieces of knowledge together over many decades by many scientists. Okay, so contribution from lot of renowned scientists are there to build up this quantum mechanics theory. So, we will discuss mainly main concept behind this development of this the quantum mechanics, and from there the computational materials. So, first the quantum nature of electrons. So, first Niels Bohr proposed that the electron in a hydrogen atom is not circulating on any arbitrary orbit, but on specific one having some specific energy or a angular momentum. Okay, and these specific energy states are called the orbitals, and for which electron does not radiate the energy, so that it gives the stability of the atoms. So, essentially energy is quantized at the same time also when the electron moves from one state to another state, also that energy gap is also fixed. So, if we give the comparison between the classical mechanics and quantum mechanics, we can do that as a form of escalator, where you are just continuously moving from one level to another level. That is the classical mechanics says that the particle can take any value, any energy value, but in the case of the quantum mechanics, it said that it can take some specific values, like if you go from one level to another level by using a lift, you can there in between two levels there is no you cannot be there. So, essentially the energy is quantized at the same time also, and that quantized energy also gives the different specific nature or the state of the electron where it can reside without the dissipations of energy. The second concept was the dual nature of electrons. So, and that was given by de Broglie, and he redefined a particles and wave as a single entity. He said that particles can behave as a wave, wave also can behave as a particles. So, apparently these are the matter wave. Okay, and he also gave the wave related property like the wavelength with the classical mechanics related property like momentum. Like momentum is inversely proportional to the wavelength, and energy also is proportional to the frequency. And using this, we come across that the wavelength should be such that it will give that specific energy. So, all the wavelength of the matter wave cannot give the stable configuration. Okay, so from there also we get that what should be the nature of the matter wave, so that the electron can be stable in a system. Then comes the Heisenberg uncertainty nature of electrons, because electrons if it behave as a wave, so wave itself essentially you do not get a specific position where the wave is. Okay, so you get it is spread on. Okay, so from that it says that there is a certain limit unto which you can simultaneously determine the position and momentum. Okay, and that is given by delta x into delta p. It should be greater than h bar by 2, where h is a Planck constant. Similar way also the delta E, that means the deviation in measurement of energy and with respect to time, again it is greater than h bar by 2. Okay, h bar is nothing but h by 2 pi. So, when a wave span into space, we can tell how fast it propagates. That means we can get the velocity or momentum, but its position is unknown since it is everywhere. Okay, let us say if you have a precisely wavelength. So, if the wavelength is fixed, that means one single wave. So, for that we can easily find out the momentum, but we cannot know where the position of the particles. Similarly, if we have to get the particular wave particles confined as a particular space, in that case also what you need to do, that you need to superimpose a number of these waves. So, it will have difference in the wavelength or difference in the momentum. So, if you just jot down to a very small space where the particle is, then you need to use a number of the wave having different wavelength. So, different wavelength means essentially also you cannot determine exactly the momentum. Okay, so that is the limit between these two the conjugate properties. So, using this, now people are thinking of how to get the energy of the particles having all these the matter wave behavior, and then there comes the Schrödinger equation. Okay, so this is kind of the postulates, but it works, and it gives that the h psi equals to Hi, where psi is the wave function, h is the Hamiltonian operator, and E is the energy. Okay, and it says that if we know the wave function, then we can get all the properties using, of course, the approximate using the exact operator. And also we can get in the Schrödinger equation is given by minus h bar square by 2m del square psi plus v psi. V psi is nothing but the potential energy. The first term is the kinetic energy, and I h bar del psi del t. So we need to simplify this. This equation we can solve for only one particle system. Okay, but materials, if you have to deal with, so it should be a lot of electrons is there. So you need to do the simplification in order to get some reasonable approximation. Okay. So first simplification we do that, forget about the gravity, relativity and time. Of course, relativity you can neglect for smaller atomic weight element, but for larger for heavier one, this relativity effect should be there. And time independent case, we can delete, so we can just omit this time. Okay, then we get h psi equals is a function of the where psi is a function of position, and h psi equals to e psi, and this h bar is nothing but the Hamiltonian operator. It consists of the kinetic energy of all the particles. So in this case, it will be for kinetic energy of the nuclei, kinetic energy of the electrons. Then potential energy means essentially the attractive and repulsive interaction between the nuclei, electron and electron. Okay. So this also is a little bit difficult to deal with, but generally the weight of the nuclei is quite almost more than 2000 times heavier than the weight of electron, and they say that the electron follows the nucleus. Okay, so we can decouple the motion of nuclei and electrons. Okay, so that is called the Born-Oppenheimer approximation. In this case, essentially we just fix the nuclear position and then we deal only with the motion of electrons. So here nuclei act as a kind of a Fougeon parameters to the electrons and also the spin. So essentially we get the total energy of the atom should be the energy of nucleus plus electron. Now energy of nucleus is essentially we are not treating the nucleus, we are just taking only the electronic part. So then the Schrödinger equation is become only the electronic Schrödinger equation. So essentially h psi all the position of the electrons and equal to e psi as a function of only the electron position. So essentially we are omitting the position variable of nuclei, and at the same time also in that case we can take the Hamiltonians only taking the kinetic energy of the electrons and electron interaction and electron nuclei interaction. Okay. Now also we can forget about the excited state, that means we can only consider the ground state, which is also another simplification. Another simplification also we can use the convenient atomic units. So the most of the parameter become 1, and the equation looks a little bit simpler and also easier to solve. Okay, so these are the simplification of this wave equation we need to do at the first place. Now a little bit more on the time independent electronic wave equation. So we are using the Born-Oppenheimer approximation. That means we are just decoupling the motion of nuclei and the electron, and we are treating only the electrons, so that first get the electronic energy for a fixed position of the nuclei. Okay, so later on also we can change the position of nuclei and also again calculate the electronic energy. So essentially this is the Schrödinger equation is a eigenvalue problem, and the psi gives it all the information, and if we use a proper operator, so that we can get the energy. So energy has to be the exact. Okay, like a magician can only operate it and get the desired observable. So we have just got it. The total kinetic energy is given by h bar square by 2m summation of the delta square. Her delta is nothing but the del square, del x square plus del y square plus del z square, which is in the Cartesian coordinate system. Okay. So the starting point for computational material science is this equation, and the ground state property of the system can be determined by solving this equation if we have a method to solve it. So we need to look for the methods. We know all the potential energy term and also we know the kinetic energy terms. Now what should be the nature of the wave function? Because particles we are considering as a wave, so you need to look at what kind of wave function you need to take. So first principle methods concern about the wavelength, wave vector and wave function of electrons. Not all wave-like function can be qualified as a wave function in the quantum world, but only some of the special one, and these special wave function are called eigenvector, because the problem itself say eigenvalue problems, and the wave functions are kind of the eigenstates or eigenvectors, and what's the energy or any observable value what we get is called the eigenvalues. So psi should be, what are the different, the nature of the wave function should be, it should be continuous, it should be square integral, because we have got the kinetic energy term, we have got the del square, so it has to be the double differentiable, and also it should be single valued for all coordinates to fit into the Schrödinger wave equation. Okay. The real physical meaning of psi can be realized only when it is squared as psi square for probability density of finding the electron, since an electron must be somewhere in the space and it should be must add up to the unity, and this is called the normalization. That means you take the psi square all over the space as the integral, then you get equal to 1. And psi must be orthogonal with other wave function in a given system, and this ensures that each wave function represents distinct physical states like 1s, 2s, 2p orbitals, and of its own corresponding to its unique eigenvalue. So what essentially is say that if you take the psi I and psi j dr integration, and if I and j are not same, then it should be 0, and which is called the orthogonality position. So that's why together it is called orthonormal. Okay. At the same time, the electrons are permeable, the fermion particles, so the psi must be antisymmetric also. So with respect to the extent of any pair of electron coordinates and spin variable as the electrons are fermions. Okay. So this also should correspond to the nature of the wave function. So there are different eigen vectors are there, and for approximation of the wave function, essentially we use certain combination of the plane waves. Okay. So what is plane waves then? So plane waves are the waves which propagates perpendicularly to wave front with a constant frequency. Okay. And it is the simplest one and the most frequently used wave functions for solid. Okay. Note that the function sin kx for some real number k has an arbitrary wavelength lambda equals to 2 pi by k, or we can take the imaginary function also, exponential I kx also we can take as cos I kx. That means psi, the plane wave basis, or let us say the wave function as a plane wave, we can take cos kx plus I kx, and also if we take the double differential of this, we get minus k square. This is also, it shows that it's a kind of a eigenvector, because you are doing the operation and you are getting a constant into the operand. Okay. So generally free electrons travel this way, like the plane wave, and valence electron in metals do similar, because valence electrons are free in metal. Okay. So more important, we can expand any wave function with many of these plane waves. So that is essentially which is called the basis function. Okay. So for starting, initially we don't know the wave function of the material, so we start with some of this the known type of plane waves, and we said that we take the combination of this plane wave and we do the energy minimization of the total system. So that, and during the energy minimization, what we do that, what are the constant with which we are just multiplying with the different plane waves, so that they get change. Okay. So that we get the lower energy. So we do the approximation by taking a combination of these plane waves. Okay. And the standing waves does not proceed, but it's vibrate up and down in the space, which gives the electrons in kind of the material, which is some of the cases where it is bound. Knowing all this, the theory behind it, the wave function and its development and all, and some of the approximation, we need to go for the calculation for the material's property or energy. Okay, using this Schrödinger equation. Okay. So as I mentioned, that Schrödinger equation you can solve it for only one electron. Okay, but most of the cases you need to do a number of electrons, so you need to go for some of the approximation. Okay. So this first approximation was the Hartree method. Okay. So despite the innocent look of the Schrödinger equation or H psi equal to E psi, solving it and calculating a property is a very difficult task. Okay. Dealing with n electrons that interact with all other electrons at the same time is just too complex to solve even numerically. Okay, which is a kind of a many body. So if you, it's behave like a crowd. In a crowd, it's very difficult to describe if all of them are interacting at the same time. So one has to resort to various level of approximation without sacrificing the parameter free nature of the first principle method. First principle itself should be parameter free. So to bring the problem down to the tractable level, it is assumed that each body is independent. So essentially we are considering that all the crowd, people in the crowds are behaving in the same way and they are kind of a quiet. And one people see the others as a kind of the smeared out or average kind of their behavior. Okay. So essentially what is that? Each body is independent and interact with others in an average way. That is, for an n electron system, each electron does not recognize each other as single entities, but as a mean fit, which is the Hartree method. Hence, n electron system becomes a set of non-interacting n number of 1 electrons, where each electron moves in the average density of the ray. So, essentially we are considering that though the number of electrons are more, but we consider the electrons one by one, and we do not consider individual interaction between the electrons. So, we just consider electrons as if it is interacting the average field played out by all the others electron. So, Hartree method essentially from n electron system, it is becoming n number of 1 electron system. Okay. So, the Hartree method treated 1 electron at a time and introduced a procedures he called the self consistent field method to solve the wave equation. So, essentially we are getting the overall the Schrödinger equations, where this UEXT is the attractive interaction between electrons and nuclei, and UH is the Hartree potential coming from the classical Coulombic repulsion. Okay. So, essentially first one is the electron nuclei interaction, and UH is the electron interaction, but in this case electron are interacting with the average field. Okay. So, that is why we are writing as a Hartree potential UH, okay, between each electrons and the mean field. So, essentially in this way, what we can get for each of the electron, now we can get their individual energy. Okay. So, the total energy will be the sum of the energy, and also the total wave function will be the multiplication of the wave function of each of this electron. Okay. So, the Hartree method fits exactly with a hydrogen atom of just one independent electrons and calculate the exact ground state energy like minus 13.66 electron volt. Okay. So, but there is certain drawback on this Hartree method. First drawback was that the electron is antisymmetric. That means, if you change the position, then also it should change its sign, or you interchange the position between two electrons, then it should change its sign. Okay. So, Hartree method produce only a crude estimation of the energy, due to it does not follow the antisymmetric principle and thus Pauli's exclusion principle, and it does not count the exchange and correlation energy coming from the n electron nature of the actual system. Okay. This exchange and correlation energy also will discuss more when we come in the density functional theory method. At the same time also, this is the major drawback of Hartree-Fock method, that also should remember that in this case we are not considering the correlation energies. Okay. The Hartree method therefore was refined into Hartree-Fock method, where the true n electron wave function is approximated as a linear combination of non-interacting 1 electron wave function in the form of a Slater determinant. In this case, essentially we are not considering taking the multiplication of it, we are taking the wave function as a kind of a Slater determinant with a normalization factor. So, that it satisfy the antisymmetric principle of electrons. Okay. So, essentially at the same time also, so you can see that if we just interchange the position of two electrons, essentially we will get the negative you can get the negative sign of the wave function. At the same time also, determinant with two identical rows or column is 0. So, if two electrons occupying the same wave function, then also it will become 0, that means it does not exist, and this also ultimately satisfy the Pauli's exclusion principle. That means the electrons with all the 4 quantum state cannot stay together in the single orbitals. Okay. So, that also it will satisfy. Okay. So, essentially in the Fock case, you need to take the wave function as a kind of as a Slater determinant. Okay. So, that it will satisfy both the exclusion principle and also the antisymmetric principle. So, earlier case it shows only for 2 electron system, but it can be a n number of electrons. So, then the general expression for Slater determinant for n number electron, if we neglect the spin variable, so it should look like this. So, essentially all the wave function, let us say n number of system, we can take that n number of the wave function for each of them, and this each wave function can be occupied by all the electrons. Okay. So, let us say psi 1 can be occupied by electron 1, 2 till n, psi 2 can be occupied by like this. So, that way we can show. Of course, you need to take the use the normalization factor, so that normalization, the wave function normality fulfilled. Okay. So, all elements in the Slater determinant must also follow the orthogonality principle and also the normality principle. That means all this orbital, it should be also the orthonormal. So, knowing all this, how to deal with the wave function, how to treat the wave function. So, you need to go for how to get the energy. okay, because you don't know the wave function at the very beginning. Okay, essentially we can start with some of the crude approximation using some basis function, and then you need to modify according to the system. Okay, so for that you need to go for the energy minimization. Okay. And for that essentially again also you need to look for the expression for the energy. Okay. Now let us rewrite the wave equation with the wave function consisting of its later determinant. Let us say this is written as a later determinant, and this is the Hamiltonian operator, and this is the energy. Okay, but what you know after doing the calculation, first thing that psi r is unknown. Okay, so you just approximate it, and from this psi r initially first you need to get the energy, and then also you need to change this this function, and also again measure the energy. Okay, so each step energy should decrease. So that is the principle. Okay, so first thing that you need to check how you can calculate the energy. Okay, so generally in quantum mechanics it is a kind of a probabilistic case. So essentially we go for instead of the numerical average, we go for the expectation value of any observable, in this case energy. Okay, so the expectation value of energy corresponding to the operator H is obtained by quantum manipulation like this. So essentially you take the quantum conjugate of or complex conjugate of the wave function and use the corresponding operator. In this case for energy is the Hamiltonian operator, and in order to make it a kind of a normalized one, in this case you need to again take the self integral. Now we insert this higher in the form of the later determinants and H of 3 energy terms in the energy equation to calculate the total energy. Okay. So for E, because we get this wave function, okay, for and also for each of the electron in the systems, now we can find out first you can calculate the total energy of the system using the overall the Hamiltonian operator operated to the wave function. Okay. So of course if the wave function is normalized, then the denominator term should become 1. Okay. So that we get energy equals to kinetic, total energy should be equals to kinetic energy, external energy plus Coulomb energy. Okay. So Coulomb energy and also the exchange energy coming from the quantum nature of it. Okay. So the Hamiltonian energy essentially this EH or Hartree energy essentially it's coming from the average electron interacting with the average potential, and each all potential coming from all the other electrons. Okay. And also exchange energy generated negative, and Coulomb energy because this interaction between the same sign, negative sign of it. So essentially we get the positive value. Now so we get the energy expression, we got the expression, the equation from which we can improve improve the wave function. But how to improve this wave function? Okay, so for that essentially we go for the variational principle. Okay, for the ground state. So in quantum mechanics there is only one ground state energy in a given system under given condition if there is no degenerate state. Okay, and any energy lower than this value simply does not exist. So that is the lowest energy, ground state energy, that is the lowest energy. Okay, so that means you need to when you start with the approximation of the wave function, the energy should be more than the ground state energy, and you need to decrease this energy by changing the wave function. Okay, so essentially it's a minimization process, energy minimization process. Okay, so if we minimize the system energy with respect to the wave function, the energy at the end will be the ground state, if you in a true sense, and this is called the variational principle. Okay, that means you vary the wave function. Okay, so that you get the energy lower and lower and lower. Okay. And how do we vary the wave function? Because now wave function we generally take a linear combination of known function, which is called the basis function, and the basis function, the combination, each combination of these the known basis again comes with a parameter or a constant value. That constant is not unknown. So what we do that we just use that this variation principle to get the unknown values. Okay. So due to the non-linearities introduced by the Hartree-Fock methods, it adopts the iterative self-consistent procedure for the solution of the wave function. Okay. Through this variational process, the initial approximated wave function in the later determinant will approach the true ones that calculate the ground state energy. Okay. So that is essentially the variational principle. Okay. So what is the self-consistent procedure? Choose a proper set of n wave function the psi I such as, so n number of psi I such as the wave function of hydrogen for an atomic calculation and a linear combination of atomic orbitals for the solid. So essentially some of the known orbital orbital as a basis set or basis function, we take it. Okay. Then we just take the combination of this. Then calculate the electron density. Okay, and calculate the 3 energy term of the electronic Schrödinger equations. Okay, and insert these values into the wave equation and solve to have a set of Ei and a new set of psi I. Okay, so repeat the, so essentially every step we are changing psi I, and in term also we are changing Ei. Okay, and each step essentially Ei should go on decreasing. Okay, so repeat the above process until self consistency is. Self consistency means you come at the end, you come at a wave function where you see that 2 conjugate iteration, there is no change in the energy. Okay, so then we say it's, or difference in the energy may be some less than the some predominant range of error. So that we obtain the Ei. Ei means energy of each of the electrons will be the ground state energy of each electrons, and its sum will be the total energy of the electronic system. So that is essentially the Hartree-Fock method in a very brief sense. Okay, what are the special statement we get from the Hartree-Fock? Thing is that the same spin electrons are kept away from each other by the antisymmetric requirement, and the Hartree-Fock treatment fully counts this quantum effect by exchange energy, and the electrons of the different spin also have a tendency to stay away from each other, because electrons are of same charge, and if there also there difference in their spin also, because qualifications will say that 2 electrons can stay in a single orbital if there are they are different spin. Okay, but spin are different, but their charge are same. So there will be some kind of the repulsion also. That part is not considered in Hartree-Fock methods. So the electron of different spin also have a tendency to stay away from each other by the same charge they have, and this is called the correlation. This is missing here, and this electron correlation is missing in the Hartree-Fock method, and this is accounted for in the DFT. So that is the one advantage of DFT. At the same time also other advantage of DFT is also there, because it is very fast compared to Hartree-Fock. Okay. Note that this scaling of the Hartree-Fock method is roughly of the order of 10 to the power of 4. Okay, so that means if you just double the number of electrons, then the time it will take maybe 2 to the power of 4 times. Okay, and thus a doubling of system will size will increase the computer time about 16 times. Okay, so these are the drawbacks, and this here you get the basic principle behind solving the Schrödinger equation by Hartree-Fock methods. Okay, now comes the density functional theory method. So density functional theory, as the name suggests, that here we use electron density as the main variable to solve the n electron problem. Okay, so earlier case what we are taking, if you have n number of electrons, so what we are doing that, so for each of the electrons now we are considering as a variable. So total variable wave function is a function of 3n variable. Each electron have x, y, z coordinate. So n number of electrons will have 3n number of coordinates. So the total wave function is a function of 3n variables. Okay, but in the case of density functional theory, we consider that the energy we can write it as a one function, single function, and which is a variable only x, y, z of the total system. Okay, so it's of only 3 variables. Okay. So the Kohn-Sham use the electron density as the main variable to solve the n electron system, and the problem has changed the 3 n dimensional equation to n separate 3 dimensional equations. So each of the electron now they have only the 3 dimensional ones with the use of the electron density. Note that there is no individual electron in the case of the density function theory, only a 3 dimensional density of the electrons. Of course, you need to use the kind of this orbital kind of procedures to find out the kinetic energy and all. At the same time also to get the behavior of different electrons, okay, from there. So those orbital kind of things is there in the density functional theory, but in the actual solution essentially we consider as a electronic density, and this density is function only with of 3 variables x, y, and z of the whole system. So time takes to solve the energy equation is less if you do it in terms of the electron density or charge density. Okay. And also we can consider the correlation energy if we have the proper functional form. Okay, the skipped correlation energy in the Hartree-Fock methods is accounted by some of the approximation. Okay, so quantum mechanical wave function system becomes an electron density. So Hartree-Fock is a kind of a wave function based method, but the density function theory is basically electron density dependent problem which reduces the computational effort drastically to the level of practical use for molecules, solid and materials. So that's why the density functional theory or DFT is the main choice of method used nowadays for modeling in solid molecules, even and materials. Okay. So essentially, so Hartree-Fock method is essentially the electronic wave function method. In this case, in the case of this density functional theory, we are not considering individual electron. During when we solve the energy equation, we use electron density as a variable, and this electron density at different position it may be different, but we can write it as a function of the position x, y and z. So electron density is the main variables in density functional theory, and this electron density again we can get it from the kind of this orbital kind of approximation of the. So this electron density is any electron system is the number of electrons per unit volume at a given point r. So which is given by this rho r. So if we take squared wave function at a point, so essentially as I was mentioning that the square wave function are also used. They are not in the true sense the wave function, we called it then Kohn-Sham function or Kohn-Sham wave functions. Those can be used to get this density, and this now at the end we can use that density as a functional, and density as that density now it's a function of x, y, z, and that density we can use as a functional form to get the energy terms. Okay, basically mostly the exchange and correlation energy terms. So if we take the square wave function at a point, so it will build up an electron density at that particular point. So essentially people also, the most difficult part, people don't understand DFT because they say that there is also a wave function, here also it is a wave function. The main thing is that wave function is there, but it is in the case of the density functional theory, the main equation we solve only in terms of the electron density. Of course the electron density comes from the wave like function is used to get the electron density. Now electron density is a kind of the measurable quantity, we can measure it. So they are observable, but wave function are not. That is also another good thing about the density functional theory. And electron density we can have for different materials, like the electron density of each silicon atom accumulate at the bond center and build up like here. So all this electron density also we can measure, okay, as a isosurface of electron density in a bulk system, okay. And also we can get the electron density as a distance from the nuclei, and we can get how many number of the electrons are there in the core and how much in the valence. And this is for the electron density of silicon. You can say that these are the core electrons and these are the valence electron, and valence electrons are not localized, it is kind of a diffuse. Okay, so valence electron essentially for silicon is 3s and 3p electrons are kind of a diffuse. Okay. So electron density as the sole variable for the calculation of electronic system is much more realistic and convenient than the wave function based statement. Okay. So we can say that all information required to define quantum state is contained in the wave function, like in the case of the Hartree-Fock method. Similarly, also we can say that the electron density decide everything in an n electron quantum systems when we deal in terms of the density functional theory based method. So electron density is important in DFT. Okay, so in the DFT scheme, we first assume that electrons do not interact with one another. Again, also this non-interaction means use also we need to introduce, like in the case of the Hartree-Fock methods. Okay, so in the we first assume that the electrons do not interact with one another, so which we call it non-interacting, and with decoupled coordinates. Okay, and the electron density is written as a simple sum over a set of square of the non-interacting k's orbital. Here is the orbital terms is coming. You should not confuse that this orbital is not in the true sense or the wave functional based orbital. So these orbitals are used to get the density, and this density is used in the energy equation. Okay, and during the iteration process we change this k's orbitals only, so that we also change the density. And this essentially we can take the square of this different wave function and sum of this, okay, to get the overall the density of the system. So if in the system if we have n number of electrons, or let's say the total occupied electrons, we need to sum of all this. Okay, so if we add up, so essentially all the electrons, but if it's a closed cell system, so in this case one orbital can have 2 electrons. So essentially that's why in this case all the occupied orbital we are if you consider it, okay, then you need to multiply with 2 because each occupied orbital have got 2 electrons. Okay. So now if we add up all the electron density over the whole space, it will naturally return the total number of electrons. Okay. So this is the total electron density of the system. So if you take all the systems and integrate it all over the space, so you should get the total number of electrons. Okay. But actual sense what we are doing, that we are just refining this psi I giving you rho r, and this rho r also should give total rho r all over the volume integral over all the volumes should give the total number of electrons. Okay. And the electron density in a system not only represents the wave function, orbitals and the total number of electrons, but it also directly related to the potential energies and thus all the properties. Okay. Like in the case in wave functional based method, we say that wave function have all the information. Similarly also we can say that the electron density have got all the information, and we can use this electron density to find out all the other properties. So now electron density as a central player, and first it was proposed by 2 theorems by Hohenberg-Kohn theorem and Kohn-Sham theorem. Okay. The first theorem of HK state that there is a unique external potential U external determining solely by the ground state electron density. What it says that there is unique external potential determined solely. So this external potential is nothing but the interaction potential between the all the electrons. Okay. So it says that unique, if the electric position is fixed, and it says that there is unique potential which is determined solely by the electron density. Okay. That means this U external is the measure of the interaction between electrons and the nuclei, and the number of electrons that are interacting with nuclei is defined by the integral of the electron density. And in an electron density profile around an atom, so this electron density profile will be different and near the electrons, near the atoms, or where the atom is not there. Okay. So in an electron density profile around an atom, the cusp shows the location of the nuclei, and the height of this cusp indicate the relative magnitude of the nuclear charge. So from this, the cusp and the height of this cusp gives you the nature of the nuclei you have it. Okay. So internal potential, the electronic kinetic energy plus the electron potential is independent of this external potential, and therefore has a universal character. So what it says that the internal potential, that means the electronic kinetic energy plus the electron potential, that means only the electronic term in the Hamiltonian operator, like the electronic kinetic energy or the electronic potential is independent of this external potential, and therefore has a universal kind of the functional form. Okay. So it's for different system the difference in the systems are coming due to the position of the nuclei only, and it says that all electrons can be the internal potential, that means the the kinetic energy and interaction energy between the electrons are kind of a universal. Okay. So that's what it says. Okay. Although its explicit formula is unknown. Okay. And this different Hamiltonian differ only by the external parameter, that means the different configuration of the system. Okay. Depending on the kind of the nuclei. Thus electron density defines the external potential and Hamiltonian wave function and all the ground state property of the system in terms. Okay. So the first theorem gives that the electron density is a kind of a central player in the case, and also the electronic part or the internal potential of the electrons is a kind of a universal. It's same for all the systems, only difference come from this external potential. Theorem 2 is that finding the ground state. How do we find the ground state? So at a given external potential, if we minimize the system energy as much as we can with the varying electronic density, then we will reach the very bottom of the energy well, yet not below it. Okay. That means we can get the ground state energy. Okay. And this is the variational principle in the framework of DFT. In the case of the framework of variational principle in density functional in Hartree-Fock theory, what is say that we change the wave function, okay, so that we go down the energy hill. Similarly, in the case of the Hohenberg-Kohn theorem, it says that we change the electron density to minimize the system energy, okay, to get the ground state. And it says that this energy as a functional of of electron density. It is a kind of a this universal one which gives the internal part and also the external part, and should be it is greater than the ground state energy. Okay. And the search can start from any points, energy calculated by any educated guess for the electron density in any possible way. So, now this electron density first we get it by using some of the basis function. Basis function means some of the known shape of the wave functions or a combination of the wave function, and those combination of the wave function first used to calculate the electron density. Okay. So, in practice for a solid we normally start with the energy calculated at the electron density generated by overlapping some of the atomic density. Atomic density, overlapping atomic density means this again overlapping atomic density comes from the orbital type, or in this case Kohn-Sham orbital types. Okay. Or first you start from the basis set, and this basis set get refined and it correspond to the Kohn-Sham orbital. So, those are the main theorem. The Hohenberg-Kohn theorem, it says that there is a exist of the universal potential, internal potential. At the same time also we can use the electron density in a variational form to get the ground state energy. Okay. Now, how do we find out this ground state 1 electron? So, for that we need to go for the Kohn-Sham approach. Okay. What we do that, the n electron system we consider is a n number of 1 electron system. Okay. So, given the two theorem of Hohenberg-Kohn, Kohn and Sham constructed by using divide and conquer approach to a fictitious system of n1 electrons or non-interacting mapping for the actual n electron or interacting. In actual case all the electrons are interacting, but in the Kohn-Sham approach I would say that the electrons are not interacting. Okay. And we are just saying that the n electron system is nothing but the summation of n number of single electron system. Okay. So, we need to solve this time independent Schrödinger equation wave function for n electron system using a full Hamiltonian. So, we are just adding up, we are just summing it up for n number of electrons. Okay. So, Hamiltonian is now just summing up all the kinetic energy of electrons, then the external potential, the external potential, and also the kinetic energy of the interaction energy between the electrons. So, this first term and third terms gives you the internal interaction, or and this is the external part. Okay. So, the last term contains various interactions that are difficult to formulate in calculable equation. Kohn-Sham had to take a detour around this problem. So, essentially one electron interacting with another electrons, it is difficult. In this case, this is not the kind of the average field as we in the case of Hartree-Fock. In this case, it says that one this need to sum up of all the electrons. Okay. So, you need to do some smart manipulation so that we get this value. Okay. So, there comes this Kohn-Sham approach. Okay. So, the interacting n electron energy of the Hartree-Fock approach with the four familiar terms of the kinetic, external, Hartree and exchange energy. Essentially, the total energy nothing but the kinetic energy, the external potential, and then the Hartree and plus the exchange. So, that is in the case of the Hartree-Fock. Okay. Kohn and Sham first assume that each electron was non-interacting at the ground state system, then they decompose the energy of interacting n electron into that of a n number of non-interacting 1 electron system under the given external energy. Essentially, we are considering that n number of non-interacting electrons, and in order to get the exact value, essentially again also we need to go for some of the functional approximation.